Hopefully, at this point, the definition of a Markov chain is something that you've seen before. Now, I'll introduce it just in terms of a little bit more formal mathematical notation. It's a sequence of random variables, call them x0, x1, x2, where the index, the 0, the 1, the 2, indicate some ordering, i.e. x1 is after x0 and before x2, and such that the conditional probability of xn plus 1 being j, given xn is I, is the same as the conditional probability that, that xn plus 1 is j, given xn is I, and the entire past values of xn minus 1, xn minus 2, and so on. So that might be quite intimidating and maybe a bit confusing, but it can be put in plain language that just says if I have a sequence of observations, the probabilities of future states conditional on knowing the present state is the same as the probability of those future states being observed given the present state and all the past. That if I know the current observation, xn, then I don't gain any more information in terms of predicting the future by knowing how I got to that point. I always think that the clearest example of a Markov chain is something like a board game. Here, this is, I would call this snakes and ladders. I think in North America it's often chutes and ladders, but the same idea that you roll the die, you move that number of squares forward, and then you may or may not take a shortcut up a ladder or a reverse step down a snake or a chute. If I wanted to predict where a player might be one turn in the future, all I would need to know is where they are now. Because then I would just say, well, with probability 1/6, they'll roll a 1 on the normal die and move on 1 square. With probability 1/6, they'll roll a 2. It doesn't actually matter how they got there. So if I were told that you were on square 41 after 11 moves, and by the way, you were on square 36 after 10 moves, and after 9 moves, you're on square 31, and so on, all of that information is irrelevant for predicting the future, apart from knowing where am I now? Oh, after 11 moves, I'm on square 41. If we have a Markov chain, very often we will get to an equilibrium distribution. And in fact, for all finite Markov chains, this is the case. So what that says is that if I left it running for a really long time, as the number of steps I was looking at tended towards infinity, then eventually it would settle down to being all future observations being effectively draws from some fixed distribution. Now, the snakes and ladders game we saw, the equilibrium is trivial because assuming a player keeps playing until they hit the finish square, eventually, with probability 100%, probability 1, the player will hit the finish square. Sometimes there is not a fixed value it reaches, but maybe some a small number of possible places it may finish, each with a different probability. Now, there are methods through eigenvector, eigenvalue methods that you may have seen to work out equilibrium distributions, but we don't always need these. Sometimes we can do them just through a visual inspection. So let's say here we've got a Markov chain and the states are A, B, C, and D. And we're going to assume that if it's in a given position, the system moves to another state with probability equal to the weight of the arrow in this diagram. So there's 4 states. If it's in A, then one step in the future, it's 50-50 if it's in B or C. If it's in B, then it's 50-50 one step in the future if it's in A or D, and so on. In this case, if I start to work out, well, if I left this for a really long time, I don't know how long, but maybe millions, maybe 1,000,001, maybe a billion, whatever it is, a very large number of moves. Then I came back and looked at it. Where would my belief be about the current state of the chain? Well, I hope this one's quite easy to see because there's no reason why it's more likely to be in A than B, or more likely to be in A than C, or anything else. Totally symmetrical in every way. So in the long run, I would expect to see each of the four states equally likely. Now, although the example on the previous slide I thought was quite a simple one to do by inspection, there are others which are not so straightforward. Now, this one looks similar, but I've changed the probabilities so that, well, two things. They're not all symmetrical, but also the weight of probability leaving a state doesn't add up to 1, so there would be some chance of it staying in a state. So it might go A to B, to stay in B, to stay in B, to D, to B, to A, to stay in A, to C, and so on. Now, I can see that there is going to be some equilibrium distribution for that, but I can't do that easily by inspection. I could do it through some eigenvector eigenvalue methods, but it's not a trivial calculation to do numerically. One thing that we can do, though, is simulation. We can simply say, okay, that diagram represents the rules of this Markov chain. Let's run this Markov chain. Obviously, we can't run it for infinite moves, but we can run it for a large number and see what we're seeing. So when I do that for this one, I'm going to pick a large value of n in the future, and then restart it, pick a large value of n in the future, repeat, repeat, repeat. And what I got was that. And when I did this, perhaps unsurprisingly, I got a quarter of the time in each state, give or take a little bit of noise.